So, as I said, this week we're just going to focus on one section, which is 6.3, and it's on graphing sine and cosine. Okay? We go nice and slow through it, so we're going to talk about all four transformations, but we're going to go very slowly. We will talk about the graphs of tangent, secant, cosecant, cotangent, but not this week. We also don't go into as much depth with those. We go into a lot of depth with these. So let me show you first what these look like. Does anybody know what they look like when you graph them? Sine and cosine functions?
Like a wave?
Yep, they look like a wave. So here's sine. I'm going to graph sine in blue, I'm going to graph cosine in red. Now, a lot of times when you graph, and we're doing a trig, you want to do zoom 7. We do zoom 6 a lot, that's the standard window. But zoom 7 is a trig. It's a special zoom set up for trig. Okay, so there's the graph of sine. It's like it's a wave. And there's the graph of cosine. What's the difference between the two? I mean, they're not exactly the same because they're not on top of each other. Yeah?
It looks like there's a horizontal shift, one left or right.
Yeah, it's a horizontal shift of one tick mark, whether one tick mark, what that really means, it's one tick mark on here is 90 degrees. But yes, it is a horizontal shift.
The crest of cosines is 0, x.
Yep, so you can look at like the highest and the lowest. So there's the highest that these ever go is 1, the lowest is -1. All kinds of things. But that's what they look like. They are continuous, meaning you never have to pick your pencil up when you draw. Just to show you guys really quick what an example of tangent looks like. Tangent is not a continuous function. There's a pattern to it, but you have to keep lifting your pencil every time you draw it. All right. So we'll look at that next time. All right. Now, because these graphs keep repeating themselves, they're called periodic functions. Basically, what a periodic function is, it's a function that repeats itself after a certain amount of time. So once you go through a certain amount of x values, you're going to see the same y values repeated over and over. And I'm going to show you visually what I mean by that. So let's take and just want to look at the graph of sine. All right, let's put that here. Now you're there. Okay. Now, what I want you to do is just focus on the section between the red lines. From here to here. Inside those red lines, that is called one section or one cycle of sine. Okay. Goes up, goes down, goes back up, and that's it. If you go beyond that section, all you have to do is copy and paste what I already drew. I just want to click on that, like that. Everything else in that graph is just a copy and paste of what's between the red lines. So when I'm saying the y values repeat over a set of x values, this is the set of x values from here to there. If you go through that many x values on the graph, which looks like it's about 4 tick marks, 1, 2, 3, 4. If you go through that many, your graph will repeat itself again. Okay, and that's called a periodic function. Nothing else we've looked at this year has been periodic. Parabolas, square roots, exponentials, anything. Okay? Nothing has this pattern where it repeats over and over. So, the length, let me make this bigger so you can see it. The length of that interval that I drew in black, right there, from left to right, that is called the period of a sine or a cosine function. Okay? It's how far you have to go on the x-axis before your graph repeats itself. This is the normal period of a sine and cosine function if you don't mess with it at all. Okay? And by mess with it, I mean you don't stretch it, you don't shift it, you don't compress it, you don't do anything to it. Just graph the basic sine or cosine function. And it will have a period of 2 pi radians. Somebody remind me, what's 2 pi radians in degrees? Yeah.
360.
360, yep. So from 0 to 360 degrees, you go through a full cycle of sine. So as I've been talking to you guys, I've kind of been using these two words interchangeably. Period, cycle. Means the same thing. One cycle of a sine graph, one period of a sine graph. No difference between those two words. The word cycle is used more in other like trades, disciplines. Is anybody in electrical? You're in electrical? So when you measure, like if you were to measure this wall outlet, you could measure the voltage. It would probably say somewhere around 120 volts. But how about the frequency of it? What's the frequency of the electricity?
You put them together.
At least 4.
You're in electrical?
At least 4 hertz.
Well, you got the right unit. What did you say?
Hertz.
He said hertz. That when you measure the frequency of an electrical outlet, it is measured in hertz. So, does that ring a bell?
I've heard
Hertz? Electrical outlet has to run at 60 hertz. If it doesn't, you have a problem. Things won't run right. So, like if you have a portable generator, sometimes generators that are kind of cheap, they may run at like 62, 63 hertz. So what that'll do in the long run is, let's say you have a motor. And the motor is supposed to run on 60 hertz, and you run it on a generator that runs like 63. Over time, it's going to cause the motor to heat up. It'll run okay for a while, but if you run it forever at that electricity that's a little bit off, it's going to wear the motor out quicker. Good generators won't have that problem. Like if you buy like a $4,000 generator, I'm not talking like a cheap $200 generator, right? But a real good one wouldn't have that problem. So what this is saying is that the electricity is cycling at 60 hertz, which means cycles per second. The alternating current is different than like the kind of current in your car. That's direct current. The alternating current, it alternates a certain number of times per second. In the US, that's what it has to be. If you're in Europe, it's a little different. I think they use 50 hertz. So you got to make sure when you plug something in that it's okay. And usually, if you look at like the, I'm talking about like those, like your cell phone charger or something, anything that has one of those black adapters you plug in. If you read it, a lot of them say something like 50/60 hertz, meaning it doesn't matter. You can use it on both. You don't need any kind of special converter. Plug it in, it'll work. And it also says like 120/240 volt. Because all the outlets in this room are 120. If you go on like a trip, other countries, they might use 240 volt. So you got to make sure whenever you plug in will work. Like that VCR, that's really old. It wouldn't work if I plugged that in on 240. It would just, I'd turn it on one time and that would be it. It would go right off and it would never turn on again. Because it's so old, it's not made to work, under both kinds of current. So I'd have to get some kind of special converter to fix it. All right? But you do see the name cycles used a lot in other trades that deal with electricity. So, was that everything on that page? Yep. All right, so when we want to, oops, I think I deleted a slide. All right, so now the next thing we want to look at is how do we graph sine and cosine? In this section, all the graphs we do are by hand. When we start looking at like the tangent and the really complicated ones, we're going to use the calculator for everything. But a wave is a little more complicated, so you need a few more points to do it accurately. 5 points is usually pretty good. 5 points for a sine wave will tell you where it starts, where it stops. In the middle, there's all your x-intercepts. It'll also give you the high point and the low point. Now, those 5 points aren't just random. They're all equally spaced. Think about if you make 5 points, if I do it in different colors, you just separated that line into 4 sections. 1, we'll do the black 1, 2, green 1, 3, and the blue 1, 4. Each section is 90 degrees apart. So in degrees, this would be 0, 90, 180, 270, 360. We won't be working in degrees in this section. We'll be using radians. 0, pi over 2, pi, 3 pi over 2, 2 pi. Those are all nicely spaced. And what I'm going to do is I'm going to give you guys a table, because anytime you want to graph a transformation, you have to know where the original starts. Because if I said to you, okay, take the sine function and shift it up 2, well, you can't shift it up 2 unless you knew where it was to start. If you know that, then you could shift it up 2. Okay, so we're gonna make a table. One for sine, one for cosine. So the x values in our table are going to be all the x values that I had up above. 0, 90, 180, 270, 360. Nicely spaced. In radians. Now, let's graph sine. And what I'm going to do is graph it from 0 to 2 pi. So what you're going to be looking at now is just one cycle. It's going to fill the entire screen. I zoomed in. But that's one cycle. All right. Look at that graph. When the x value is at 0, what's the y value? 0. Goes right to the origin. Don't worry about cosine. I'll just make this bigger, so just focus on that. All right. So 0. How about a quarter of the way through the cycle? What's my y value? 1. How about halfway through the cycle? 0. So we're at 1, we're at 0. 3/4 of the way through the cycle?
-1.
And then all the way through.
0.
Back to 0. So there's your table for y equals sine x. Any transformation that we do is going to start there. Okay. And we'll use that to figure out where we're going to move to. Now, cosine. I'm going to pick the same x values again, because we want to have nicely spaced x values. But now, let's put in cosine. Where does the graph of cosine start? Eric? It starts at 1. And then a quarter of the way through the cycle, where am I at? 0, then negative 1, 1. Yep. So it's the same y values, but they're in a different order. Cosine starts at 1, sine starts at 0. And you can't mix those up. When I give you guys a problem, if it's a sine problem, you got to go to the sine table. If it's a cosine problem, go to the cosine table. Also, while you guys are copying that, some of the applications, besides electrical, I mentioned that, you can also get into sound frequencies. So a sine or a cosine wave is a perfect way to model a sound frequency. So, let's see if I can find something for you. Let's try typing it in here. What I'm doing is I'm looking for a program that I have. It does something. Okay, so what you're looking at there is a picture of sound. That's my voice. Now, it doesn't look like much of a sine or a cosine wave because I'm changing the volume, I'm changing the pitch. I'm not talking in a constant sound. But if I whistle, okay, that will make a constant sound. I'll try to keep the volume the same, and you should see a nice sine wave. So let's see. Kind of moving a little bit, but it was a nice sine wave. So, okay. Maybe you're too far away.
No, I think it's directional.
There you go. So you get a nice sine wave, and what we can do, we can look at exactly what the frequency is when you're making that sound. So right now the frequency is bouncing all over because I'm not talking at the same pitch. But if I whistle again, about 1.26, 1.27. So now, if I had a device that makes sound frequencies, I could tune it to 1.26 kilohertz, play the sound, and it would sound exactly the same as the pitch of my whistle. So that's another device. A lot of times, I think in engineering, they have these as boxes. It's an oscilloscope. So you can actually hook it right up to what you're doing, either with electricity or with sound. You could put a microphone in it, and it'll show you the frequencies. Okay, what you're looking at here is a picture of all the frequencies in the room at the same time. You're not looking at a picture of a single frequency. It's showing you every frequency. So you can see up around like 20,000, 15,000 hertz. There's no frequencies in the room that are that high pitch. Most of like the frequencies, like vocal frequencies, are under 2,500. And even the frequency of my voice is a lot lower than the pitch of my whistle. So human voices are usually below 1,000 hertz. Right? Yeah.
You ever seen the video? Someone hooked a microphone up to the x-axis and one up to the y-axis, and they make songs that draw like special shapes, and it's pretty cool.
I haven't seen it. Interesting. Yeah, I know there's something on like Windows Media Player they used to have where if you play a sound, it does graphics on the screen in response to the frequencies that are playing.
Yeah.
It's like this like psychedelic kind of effect thing. So I don't know if it might be kind of like that or.
It's kind of like that.
Yeah.
But they made they had like big patterns of repeating shapes and like.
Yeah.
It's so cool. I'll try and email you the video.
I know another thing you can do, and they have it at the Museum of Science in Boston, is they have like a metal plate, like this. It's on a pedestal. Under the metal plate is a speaker. They put grains of sand on top of the metal plate. Has anyone ever seen that?
They have it with the like violin bow.
Yeah, exactly. And if you play frequencies, what happens is the grains of sand kind of vibrate around and they make a pattern depending on the frequency that you play. It's pretty neat. Different frequencies have all kinds of complex patterns that just start to develop because of the vibration. It's pretty neat. So if we have time, maybe we can take a look at that. Okay, does everyone have these two tables? So one for sine, one for cosine. So for today and tomorrow, this will always be true. This will not be true on Wednesday. But the idea is, when I give you a problem, it's going to have a single transformation in it. I'm only going to do one thing. So maybe I'll give you one today where you shift left. That's it. You're not going to shift. If you shift left, that's the only thing you're going to do. So what that means is one column, either the x's or the y's, will change. And since that's the only transformation you're doing, the other column will stay the same. Now on Wednesday, we're going to get into multi-transformations. So I might give you one where you shift left and up. Now everything's changing. If you shift left, there's your x values changing. If you shift up, there's your y values changing. Okay? So you'll change both at the same time. But for today and tomorrow, this will always be true. One column will change, one column will stay the same in those tables I just gave you. All right, so everything I talked about up until now is just kind of general. Now I'm going to get into specific transformations. We're going to do two of them today. We're going to do phase shift, and then we're going to do vertical shift. So we're going to do the two shifts today. Now, anytime that you do what operation, it's a shift. Yep. Add or subtract. One is left, one is right. Okay. One is up, one is down. Depends if it's vertical, depends if it's horizontal. Okay. So phase shift. Most of the transformations that we study in trig have a different name, but the idea is still the same. It's called a phase shift. What does it really mean? It's just a translation left or right. Okay, so don't let the name confuse you. Phase shift, we never mentioned. Yeah, we've done phase shift. We just never called it a phase shift. It just means move left or right. The only one when we do trig that doesn't have a special name is a vertical shift. The vertical shift we just call vertical shift. But the other ones have special names. And I'm just going to add to what Jared said a little bit. He said when you add or subtract, it's a phase shift. I'm going to say add or subtract inside the function. Anything you do inside in the argument, what's in the parentheses, that's your horizontal. Anything you do on the outside of the parentheses, that's your vertical. Now, we should be able to figure this out because transformations work exactly the same way they've done all year. If you subtract inside, which way is it going to move? Left or right?
Right.
It's going to move right, correct. Minus is going to shift everything to the right. It's the opposite. It's always been the opposite. It's still the opposite. Minus shifts right, which means plus is going to shift left. How much? Depends what you add or subtract. Technically, you can shift by any amount you want. We usually shift by a 45 degree, 90 degree, or 180 degree. Those are the common phase shifts that we do. If you wanted, could you shift by 93.4 degrees? You could. That's just not a common one to do. So now that we know the name of it, let me go back to the graph of sine and cosine. And you guys already kind of picked up on the fact that sine and cosine were, you use the word horizontal shifts, but now you know the technical term, phase shifts. They are phase shifts of each other by exactly 90 degrees. Meaning if you take the one in blue and you shift it to the right 90 degrees, you'll get the one in red. So let's do that. I can do it in radians, but I'll do it in degrees. So I want to take the one in blue and shift it to the right. What operation would I use to shift it right? Minus. Watch what happens now. I'm shifting cosine 90 degrees to the right, and then I'm going to draw sine. But I'm going to do zoom 7. So if you notice your graph looks like this, it's because you changed between degrees and radians, and you forgot to fix your window. So let's go zoom 7, and now we'll be okay. Okay, so remember, that's cosine shifted to the right. Now look at sine. How do they compare? They're the same thing. It's tracing right over it. Okay, so what that basically means mathematically is anything you can do with sine, you can do with cosine. You can, if you know one, you can use it to do everything, because they pretty much are the same kind of thing. All right, so next step, we're going to try to make our graph. We need a table. Okay, I want to have 5 points in the table. For a phase shift, which column is not affected? The X column or the Y column?
Y column.
The Y column. The reason the Y's are unaffected is because we are moving left or right. You're not moving up or down. So the Y's are going to stay the same. Now, unfortunately, when the Y's stay the same, that means the X's are going to change. Well, go back to your table for a second. I mean, I don't know about you, but if I look at these two columns, I think the X's are more complicated. They're all fractions, and they all have pi. So, unfortunately, when we do a phase shift, you're going to have to deal with all the fractions with pi. So, Y's are going to stay the same. To find the new X's, you're going to determine what has been added or subtracted. Okay, so look at like example 1. What's been added or subtracted in example 1 inside the argument? Oh, Brandon? So what's been added or subtracted inside the argument? Example 1, right hand side. You're subtracting pi over 2. Because it's subtraction, that tells me it's a phase shift. And it tells me that it's to the right. So now, we know that this graph should move to the right. Because it's the opposite. We've done that. If you have a coordinate and you want to move it to the right, what do you have to do to the x value? If you want to push it to the right, take the x value, yeah? Well, if you subtract a number from the x value, that's going to make it smaller. That's going to move it to the left. So you have to add, right? That's why the directions say, look at what's been added or subtracted and do the opposite. Do you always do the opposite for a phase shift? Yes. Do you always do the opposite for every transformation we're going to study? No. But for a phase shift, you do. So look at what's been added or subtracted, and then do the opposite of that. And when I say original x's, I mean go back to the table I gave you in the notes. Okay, so now we'll look at our first sketch. Okay, I'm also going to show you how I grade this kind of problem. The graph itself is worth very little credit. It's worth something, but not much. What I'm really looking for is the table. think on your test, the table is worth 10 points per problem, and the graph itself is worth 1 or 2. So, let's make our table. Okay, first thing we can do, the quickest thing, is just fill in the column that stays the same. Someone remind me, which column is unaffected by a phase shift? Yeah, okay. Which ones? Unaffected. Not going to change at all. Yeah? The Y's. Okay, remember, we are not moving up and down. A phase shift means left or right. So what are my Y values for the sine function? Yeah?
0, 1, 0, -1, 0.
If you write that down, you're going to get 5 points for that part of the problem. 1 point for each Y value you just got right. Now we need the X's. Okay. I'm going to put the originals over here. Can someone remind me from the sine table, what are my original X values? Yep.
0, pi over 2, pi, 3 pi over 2.
And now, what do the directions say to do to each one of those? Yeah. Let's go back. Add. So look at what's been added or subtracted. In our case, we've subtracted, and it says do the opposite. So what I'm going to do is plus pi over 2. No decimals. I don't want any decimals here. So plus pi over 2 to all of these. I'm going to put a box here, and that's going to represent my final answers. All right, first one, that's not bad. What's 0 plus pi over 2? Yep.
Pi over 2.
Yep, pi over 2. Now the next one is fine. It's already got a common denominator. What's pi over 2 plus pi over 2? Yep. 2 pi over 2. Right? So you could put 2 pi over 2, or just pi. I'm going to reduce it. I'm going to come back to what we just said in a minute, though. But yeah, I would go with pi. Now the third one.
3 pi over 2.
It's going to be 3 pi over 2, because you need a common denominator. I'll do this one off to the side, so if you're wondering how Zach got 3 pi over 2, all you have to do is double the top, double the bottom. 2 pi over 2 plus 1 pi over 2 is 3 pi over 2. How about the next one? 3 pi over 2 plus pi over 2. Good.
2 pi.
Yep. 3 pi over 2 plus 1 pi over 2 is 4 pi over 2. Or 2 pi. Now, I'm going to go back to the version before you reduced it. I want you to notice something. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. What do you think the last one is?
3 pi.
Don't think too hard. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. 5 pi over 2. Now, that's going to be one cycle. Okay? You don't have to sketch another cycle. If you did, all you'd have to do is continue this pattern. So like if you have to take the class next year and they say, you know what, we want you to sketch 2 cycles. Okay, well there's one. 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi. I could keep going. And then continue the pattern in the y column. 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0. You can continue this pattern forever and get as many cycles as you need. Just keep the pattern going. Okay, so now the way I would grade that, you get 5 points for the x's, 5 points for the y's. So 10 points for the for that table. Questions on the table? Now, if you don't label your axes on grid paper, what is it always assumed you're going by? If you don't put any labels. Yeah. Units of 1. Okay. We don't want to go by units of 1 because these numbers are pretty bad, right? Pi divided by 2, that's 1.57, 3.14, 4.71, 6.28. Those aren't good numbers to use. The only rules when you're labeling graph paper is you have to be consistent. So like if you had a number line, you can label by 3s if you want, as long as you go by 3s the whole time. What you can't do is something like this. You can't say I'm going to go by 1s, and then I'm going to go from 4 to 9, and then I'm going to go by 3s after that. No, that's no good. So just make sure you use things that are consistently spaced. Now, these original values, 0, pi over 2 pi, 3 pi over 2, 2 pi, were they all evenly spaced to begin with?
Yes.
Yes. If you take 5 numbers that were all nicely spaced and move them all the same amount, are they still nicely spaced? Yeah. So you can use these numbers to label your x-axis. Let's put 0, pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2. Perfect. If you want to know what they are in degrees, that's 0, 90, 180, 270, 360, 450. It's plus 90 each time. Now, what's the highest and lowest we have to go on the y-axis? Emily? 1 and negative 1. So technically, I don't need to label my y-axis because I'm going to go by 1s. Whenever you go by 1s, you don't have to put a label. But just to be extra clear, I'll put it in. Okay. And now plot all your points. I'll make it bigger again after so you can see it better. Pi over 2, 0. Pi 1. 3 pi over 2, 0. 2 pi is negative 1. And 5 pi over 2 is 0. Now, remember, it's a wave. So try to make it look like a smooth kind of curve. Perfect. There's your graph. So that's the new one. Here is, you don't have to sketch this one, but I'm just showing you the original. So red is the original, black is the new one. So did the black one shift to the right from the original?
Yeah.
Yeah, that's exactly what should have happened. Because minus means shift to the right. And it shifted 90 degrees. And that's a phase shift. Questions on that one? Okay, we'll try a couple more phase shifts. This is the hard one for today. The vertical shift is easy because the arithmetic is with 1s, 0s, and negative 1s. So when we do vertical shifts, you're just adding and subtracting to a 1 or a 0 or a negative 1. Much easier. Right, let's look at that. Y equals cosine x plus pi. We are adding inside parentheses. What kind of transformation is it when you add inside the parentheses? What is it? Phase. And can anybody be a little more specific and tell me which way? It's plus. Yeah? To the left. Okay, so this is going to move to the left. Since it's moving to the left, there's no vertical movement in this problem. So my y's stay the same. Now, just be careful. Grab the y's from the cosine table. What are my y values for cosine? And after a while, you'll probably be able to picture these in your head. Like when I think sine, I picture that. When I think cosine, I picture that. Roughly. Yeah.
1, 0, negative 1, 0, 1.
Okay. So there's your y values, 5 points for those. Now I'm going to do something to my x's, but I'm going to write the originals first. How about my original x values? Yeah.
0.
Yeah.
Pi over 2. Pi. 3 pi over 2.
2 pi. Perfect. You wouldn't get any points for those. That's good. You need them, but they're not the final answer. I'm going to put my final answers in the box. What am I going to do to all those x values? Yeah. Subtract pi. We want them to all move to the left. The only way they can move left is if you make them smaller. Minus pi, pi, pi. Now, 3 of those are pretty quick because they already have common denominators. Negative pi, 0, pi. And if you want to be clever about it, the other ones are just halfway between because they're all equally spaced. But if you didn't notice that, pi over 2 minus pi over 1. Emily, what's my common denominator? Pi over 2 minus pi over 1. 2. So let's go like this. And Elias, what's pi over 2 minus 2 pi over 2?
2.
Yep, pi over 2 minus 2 pi over 2.
No.
So when we subtract, does the denominator change? Right, denominator stays the same. So 1 pi over 2 minus 2 pi over 2 is negative 1 pi over 2. How about the next one? What's 3 pi over 2 minus pi? Yeah, pi over 2. And the pattern here is the numerator is going up by 1 each time. That's negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2. You could keep going. Right? So you get 10 points on the test for that table. Okay, now our graph. All right, we have a couple numbers in the negatives, so we got to start 2 over. Right, let's do negative pi over 2, 0, pi over 2, pi, 0, 1, negative 1. Again, technically you don't have to label the y-axis in this problem. Okay, so my values are 1, 0, negative 1, 0, 1. 1, 1, 0, negative 1, 0, 1. Now, this is the one, sometimes people don't draw it right. Looks kind of like a V. But remember, it's just the middle part of one of those waves. That's what it should look like. It should not look like this. It should have a curve to it. Right? So try to make it look like it has a little bit of a curve. Just like that. And that's your cosine. Okay. Any questions on it? Okay, so we did a shift with cosine, and we had a plus. We did a shift with sine, and we had a minus. Let's do one more with sine, and we'll do a plus. And then we'll do our last transformation, which is for today, which is vertical shift. So Brandon, what kind of transformation is that? Yeah, it's a phase shift, and it's plus, so it's going to go left. So x's are going to change, y's stay the same. Jacob, what are my y values for sine?
0, 1, 0, negative 1, 0.
Yep. There's my y's. Here are my x's. Pi over 2, pi, 3 pi over 2, 2 pi. Remember, those are just a starting point. They're not the answer. Yeah, I'm just going to give myself one more room here. What am I going to do to all my x values? You got a minus pi over 4. So you're going to need common denominators on all of these. But the nice thing is, once you notice a pattern, you can just go with the pattern. You just got to figure out the first couple. And then you should see the pattern. About Kara, what's going to be my common denominator on all of these? 4. Now the first one you don't really need it. 0 minus pi over 4. It's just negative pi over 4. Okay, next one. Pi over 2 minus pi over 4. Common denominator there?
4.
4? Let's go like this. Times 2 times 2. What's 2 pi over 4 minus 1 pi over 4? Pi over 4. Now, does anyone think they know what the next one is going to be? It's got to have to be the same difference between the first two as it is for the second. Yeah?
3 pi over 4.
3 pi over 4. And the next one? I mean, be honest. 5 pi over 4. And how about the last one? Yeah.
7 pi.
Yeah. The pattern is odd numbers in the numerator. If you were to keep going, the next one would be 9 pi over 4, 11 pi over 4, 13, 15, 17. That's the pattern. Okay. Questions on the table? Now, this is one when people are graphing it, they mess up the number line sometimes. What number is in front of negative pi? Like negative 1 pi?
1.
Negative 1. I'm going to make a list here. Negative 1, 1, 3, 5, 7. Those are the numbers that are the kind of like the coefficients of pi. Let's put those on a number line. And then let's go like this. Where could I put negative 1 on that number line? Yep.
1 unit left of the 0.
1 unit left of 0. Where would I put the next number?
1 unit right at 0.
Okay. Now, looks like they've all just been 1 apart. So would the 3 go right there? No. You can't put the 3 there. You have to skip. Because technically you skipped this too. 0 wasn't a number in the list. But the problem is 0 is always already labeled for you. It's the axis. You can't change that. So 0 is already there. So 3 goes here, 5 goes here. When you label the ones we're doing, it's exactly the same thing. Pi over 4, pi over 4, pi over 4. There's no difference. Right? You have to put the labels exactly the way you would do as if they were just that. Okay, let's put those labels in. Negative pi over 4. 0 is the axis. Pi over 4. 3 pi over 4. 5 pi over 4, and I think I need one more line. 7 pi over 4. Any question about why I put those labels where I did? You'll know if you make a mistake, because if you put your labels in your wrong spot, your graph might look like this. It's like part of it is going to look squished and the other part looks stretched out. It doesn't look right.
Is that true for all things if you divide by 4?
Basically, it's true anytime 0 is not in the x list. And you might say, well, okay, we had 0 here, but you didn't do that here. 0 wasn't in the x list. Yes, technically it is. 0 would be the next one up. So when I say not in the list, I also mean if you were to continue it, like you would hit 0 as the next value up from that one. Now, in this problem, 0 would never be in this list. I don't care how far up or down you extend those x values. If 0 was going to be in the list, it would be right there. And it's not. So if you skip 0, that's when this usually happens. Okay. 0, 1, negative 1. Okay. Now we've got 0, 1, 0, negative 1, 0. I usually, when I go to graph it, I just kind of memorize the y's. Because for me, I usually have to scroll up and down on the smartboard. So if you can remember the pattern, it helps do the problem quicker. 0, 1, 0, negative 1, 0. It's okay. There's my graph. It's a little off. Okay. So any question on that? So that was a small shift. Pi over 4 is the smallest one we did. That's a 45-degree shift. It's just a little bit. Okay, and last thing we'll look at, where the arithmetic is much, much easier, is a vertical shift. So it's still a shift. So you're still adding or subtracting. But what's the difference now? What makes this vertical? Yeah?
Moving up or down.
It's moving it up or down on the y-axis. And how do you know it's not a phase shift when you look at that? Yeah.
It's not X.
Anyone else have a thought? Yeah?
Can you tell if it's like not in parentheses?
It's not in the argument. Correct. It's the difference between doing this and doing this. One time you're adding the 10 to the argument first and then doing the function. Here, you're doing the function right away and then adding to the result. Okay? That's the difference. So what you add or subtract is outside the argument. And what you see is what you do. Add moves up, subtract moves down. Okay? So as Emily just said, we are moving up and down. What column is affected by movement up and down? The y's. So this time the y's are going to change, which means what stays the same? The x's. That's great when the x's stay the same, because now you don't have to deal with any of these fractions with pi. Every answer that we do for a vertical shift today, I can already tell you the x column answers. 0, pi over 2, pi, 3 pi over 2, 2 pi. Every single vertical shift for today. So copy your x's down from the original table. Now, the y's are going to change. I use the letter D. Okay, D is whatever number you would add or subtract. So like in this problem, it's going to be 2. In this problem, it'll be -3. Now, with a vertical shift, do you do the opposite? Or just do it the way it is?
Do it the way it
Just do it the way it is. That means if you see plus, you do plus. If you see minus, you do minus. For a lot of students, when I teach this in Intro to Trig, it's the first time they've ever seen transformations. So they're not as familiar. But you guys have done transformations like 6 or 7 times now. So you should know by now, vertical shift, you don't do the opposite. Okay, so again, super easy arithmetic. You're going to add a number to a 1, a 0, or a -1. That's it. Okay, so two problems left. And then if we have time at the end, I'll stop the video and I'll show you guys what a phase shift sounds like. I'll play a phase shift in here and you can hear it. Vertical shift is not something I can demonstrate for you. I don't know any connection between a vertical shift and sound frequencies. Every other transformation I do. This one I don't know if there really is one. All right. First thing, how do you know that that is a vertical shift and not a phase shift?
outside the argument.
Outside the argument. What if I did this? Is that a vertical shift or a phase shift now?
Still fair.
Still vertical. What if I did this?
Still vertical.
Still vertical. What if I did that?
Phase.
That's phase. When you group your number and letter together, that's a phase shift. No parentheses at all. It's not grouped. It's vertical. So, what column stays the same? X's. What are my X values?
Zero.
Mm-hmm.
Pi over 2. Pi. 3 pi over 2. And 2 pi.
Now, let's put the original Y values off to the side and then see what's going to happen. Kaya, what are my Y values for cosine? Yep.
0, -1, 0.
And 1. And now, what am I going to do to all of them? Just add 2. That's it. You're not going to have to worry about common denominators, anything like that. Add 2. So, Eric, what are my new Y values?
3, 2, 1, 2, 3.
3, 2, 1, 2, 3. So there's your table. Now let's make our sketch. Here's my y-axis. And my x's. Just put them right here. I try to not put the labels where I'm going to have to draw over them. Because then if you draw through your labels, it looks confusing. Pi over 2, pi, 3 pi over 2, 2 pi. And now, what's the y column? 3, 2, 1, 2, 3. 3, 2, 1, 2, 3. There we go. So that's going to be a cosine function shifted up 2. Any questions on the graph there? Hey, what's happening here? If I just said to you on the test, describe the transformation. Yep.
Down 3.
Shift down 3. Which column would that affect? Y's. Is there any question on how you would do this one? Just take your original y, 0, 1, 0, negative 1, 0, and minus 3 from all. No question on how to do it? pretty straightforward. Okay, so homework tonight, it's gonna be a worksheet, but I put them on the board so that way if somebody's watching the video, they can see what the problems are. Alright, so I'm gonna give all those to you already printed on a worksheet. Okay, a couple reminders. My extra help is gonna be Wednesday because we have the test on Thursday. And progress reports, those are done. So if you checked it online, you're not sure why your average is what it is, come see me. We can chat about it.